Today, I'm excited to talk about Beaver, which is one of the largest rodents in the world. And I also want to share how Beaver inspires us to enable practical partial snapshots for distributed cloud services. So this is a little bit theoretical, but I hope you'll still be intuitive and interesting to you. Okay, so I want to tell you about a class of distributed algorithms. So let's consider a simple setup, which is where you have an application that requires coordination among machines. And so we basically have something called events, such as message send, receive, and local computation steps, but also states, which gets updated and distributed across machines. So essentially, snapshot algorithms allow us to capture a consistent global view of such distributed states. So many problems in distributed systems boil down to determining the global state across machines. Therefore, distributed snapshots are actually essential to ensure that we have correct operations and also reliable results. So how to achieve that? The classic method is the seminal Shanghai-Lamport algorithm, which is proposed decades ago. It also appears in almost every distributed system textbook. So here I'm going to give a simplified description of the protocol. So consider a minimal example where we have two nodes that communicate with each other through some messaging channel. And here we visualize their event timelines. At the high level, these protocols start with an out-of-band initiation, and once a node enters a snapshot, it marks future outbound messages to propagate the causal relationship. And when the node receives a marked message, it will snapshot its local state and then marks outbound messages as well. So finally, when all the nodes have taken their local snapshots, we can collect their states to form so-called global snapshots. So with it, the recorded values guarantee causal consistency, which conceptually means that if a snapshot includes the states of effects of an event, it must include any event that leads to it. So these protocols have been simple, effective, and widely known for decades, but do they solve all of the problems? Unfortunately, one fundamental assumption underlying is that the set of participants must be closed under causal propagation. So another way to put it, they presume an isolated universe of nodes and require coordination of all. However, such assumption mismatches the reality of modern cloud deployments. Why is it the case? So think of yourself as a manager of an application, and often you are faced with modular services with increasing complexity in their dependency graphs. And besides, many of these services may be owned by a different team, organization, or hosted in an inaccessible infrastructure. And what's more, even if you are a well-resourced developer, which can control everything in-house, the instrumentation itself can also be costly, as you need to consider all components involved. And worse, the internet client of the service can also be a source of hidden causal relationships. So in fact, previous studies have shown that such external traffic can account for a sizable portion of the total traffic volume. So in the end, it's unrealistic to assume zero interaction with the external world, nor feasible to ensure full participation. So given this, let's see what's wrong with the classic protocols. So consider, for instance, now we have an external front-end node that interacts with two backends of interest. Unfortunately, the message marked in red now impose hidden causal relationships that are totally invisible to these existing algorithms. So this can easily render classic snapshots inconsistent. So now, because now we have event E2 in snapshot, but E0 that leads to its effect is not included. So this violates the consistency requirement. So as we can see, that interaction even with a single non-participating node can render all snapshots useless. Observing this gap, we ask the question, can we capture a causally consistent snapshot where only a subset of the product system participates? In this slide, we present Beaver, which is the first partial snapshot protocol for distributed cloud services. In partial snapshot, nodes are basically divided into two groups. The in-group includes the machines of interest, and the out-group includes all other machines without control, whether it's in the same data center or in a broad internet. So Beaver basically provides to services the same abstraction as classic snapshots, while extending the guarantee to cases with an arbitrary set of external machines. Besides, Beaver achieves it without any blocking operations, such as buffering or delaying user packets. At first glance, this seems to be an infeasible target because we have no control of external machines, but also we have this non-blocking requirement. The external interaction can basically break the guarantee in arbitrary ways. Then how is it even possible? Here we learn from Beaver, which are known for their engineering expertise in building dams. So now, what if we have something similar that sits in between the in-group and the out-group that has visibility into the external traffic? To see how it works, let's revisit the previous example. So Beaver introduces this so-called logical gateway that handles all inbound traffic originating from the out-group. And on a new snapshot, it first initiates the gateway out of band, then it marks subsequent inbound packets to indicate a new snapshot. The in-group nodes then proceed with traditional snapshot operations. So in contrast to the previous case, this indirection with Beaver's gateway results in correct snapshot time points. Basically now, backend 1 node takes a snapshot before E2 event rather than be after, and is now consistent. We also formalize this intuition to what we call monolithic gateway marking and prove its correctness. So we found that it has two valuable properties. First, the correctness holds even if the causal dependency is formed by multiple external hops, or even if an element of the chain is a human. Moreover, the gateway only needs to observe packets entering the in-group, and it doesn't require any tracking of the dependencies carrying to the out-group. So this idea is actually conceptually simple, but there's still two outstanding questions. First of all, how to instantiate the gateway in today's public cloud data centers? And secondly, how to handle the presence of multiple gateways that are common in the real world. For the first question, rerouting all inbound traffic to the gateway for the target service is similarly expensive. So fortunately, we noticed that cloud data centers already place layer 4 load balancers, also known as software load balancers or SLBs, to handle the inbound traffic at virtual IP granularity. And these are basically a set of dedicated servers or programmable devices responsible for load balancing the traffic based on destination virtual IP. So the diagram shown here actually shows related traffic flow. For instance, for VIP1, any inbound traffic, whether it comes from the internet or another VIP, VIP2, needs to go through the responsible SLB as shown in the arrows in solid lines. So again, similar to Beaver that constructs dams using locally available materials, such as rocks and tree branches, here we exploit SLBs to execute gateway marking logic at near zero cost. So one might wonder, how about the outbound direction? In reality, the outbound traffic typically bypasses the SLBs to minimize the load, as shown in these dotted lines originating from VIP1. As we kind of foreshadowed in the previous slide, Beaver is actually compatible because it guarantees consistency without needing any processing of the outbound messages. So of course, assuming that a single gateway server can handle all incoming traffic is also infeasible. In reality, multiple servers are necessary to handle typical data volumes or simply to provide fault tolerance. So how does Beaver achieve it? Before diving into the solution, let's look at the implication of multiple gateways. So let's again consider the case with two gateways now. Similar to the previous case, the message enters gateway 0 and it gets marked, which triggers the backend 0 and the message back to the front end. However, as these SLBs are actually asynchronous, the other gateway, gateway 1, can enter the snapshot mode late. So this results in an inconsistent snapshot, which we are familiar with, where event E2 is included in the snapshot, but E0 is not. Well, one straightforward idea to handle this is to enforce so-called consensus across SLBs. That is, to let SLBs to block inbound messages and only resume the forwarding after all SLBs have committed to the new snapshot. Unfortunately, this method introduces high overheads, such as increased response time for the applications, or just simply extra buffer resource capacity. So we ask the question, can we get both consistency guarantee, but also without any blocking overheads? Beaver achieves it by designing a novel primitive called optimistic gateway marking. In the next few slides, I will give an intuition of how it works. So we start by considering when the worst case violation might happen. And we actually observe that causally relevant messages actually require a message chain to form, from a gateway to an in-group node, then to an out-group node, and then back to a gateway. So if we consider the time gap between the first and last SLB snapshot initiations, an intuition is that if this value is sufficiently small, in particular smaller than the time to form the external causal chain, then the snapshot is actually naturally consistent. It turns out we can formalize this intuition again and prove its correctness. And moreover, we also observe that this condition holds in exceedingly high probability in public cloud environments. The paper contains more details, but at a high level, the left-hand side can approximate 0 with proper placement of the controller, whereas the right-hand side incurs higher values because it involves at least 3 trips across the data center fabric, in addition to processing overheads and so on. So the implication of this is that we can actually execute optimistically and yield consistent snapshot in most cases. And now the key is really to detect when it doesn't hold. Beaver safely detects a gateway violation that may have occurred by comparing the left-hand side and right-hand side values using the theorem. So the right-hand side is actually relatively simple to handle. Now operators can just determine the lower bound offline because dynamic network conditions such as failures or congestion can only add to this value. The left-hand side measurement is slightly more complicated, and we don't have time to go into details, but the high-level idea is to leverage a single clock source to measure the safe upper bound. So this approach, of course, may lead to more false positives, that is, rejecting snapshots that are actually consistent. But actually, this is fine because it doesn't affect the correctness, first of all, and also user can simply just retry the operation with Beaver at near 0 costs. So in short, when there are multiple gateways, Beaver exploits the regularities of the data center network for optimistic execution and then rejects snapshots under worst cases. So this allows Beaver to guarantee correctness without any form of blocking and their associated overheads. So the paper also contains more details about the detection protocol as well as other Beaver mechanisms. We also evaluate Beaver through a prototype on a cloud data center testbed, considering different outgroup placement, ranging from those in the same data center at a different region, or on the internet. As Beaver operates mostly with the optimistic execution model, it also incurs minimal additional logic. And the paper also contains details of results, but as a quick overview, Beaver sustains high snapshot rates under typical scale for in-group services. It also invalidates less than 5% of snapshots, even under worst-case scenarios. And moreover, Beaver incurs 0 impact to existing traffic, as it eliminates any blocking or delay operations on the data path by design. And finally, Beaver's abstraction enables a wide range of potential use cases, such as integration testing, deadlock detection, garbage collection, and so on. Due to limits in time here, I'm going to give an intuition about one of these potential cases. So say now we are running ephemeral storage service, which is for serverless analytics, which performs garbage collection based on reference counts. So here, the serverless runtime that basically access the KV store for data exchange, and we also have no control over them. Consider a message pattern where lambda2 here first put the key value into the backend, and then invokes another lambda1, which gets the value. And lambda2 then terminates the execution after dereferencing the key. And finally, lambda1 also dereferences the key at its epilogue. A classic snapshot may take an inconsistent snapshot, as shown in this diagram, because fundamentally, such external causality is invisible to it. So this leads to a reference count of 0 and an unsafe decision to recycle the key, which is still under use. And in our experimental setup, the invalid dereference call percentage can be as high as more than 30%. So in contrast, Beaver guarantees correct observations and will identify that lambda1 is still keeping an open reference to the object and ensures safe garbage collection and consistently results in 0 invalid calls. So to summarize, Beaver formalizes, designs, and implements the first partial snapshot primitive. It also incurs near 0 cost by tight coupling the distributed system design with the regularities of the data center environment. So with that, I'm happy to take any questions.